what we're really getting into today is kind of a bridge. We're bridging between the activities that we want to talk about on Monday with kind of what we were talking about on Wednesday with relation to masses and percent compositions. And what we'll find is that Monday's lecture will put together the two concepts to help us solve problems about compositional material in compounds. And help us to find the formulas of those compounds with that information. So thus far, we've kind of talked about things in two different ways. We've talked about things on the microscopic scale, where we talk about, okay, an individual molecule has this many atoms of this element and this many atoms of that element. Or we have particles that we're concerned with. I've got 50 particles of calcium hydroxide. On the other side, we've talked about things in the lab, mostly on the macroscopic scale. I have 100 milliliters of acid. I have 50 milliliters of water. I weighed out 0.5 grams of rock salt. Those are all massive amounts. What we haven't talked about is those two worlds, the microscopic atoms, molecules, particles, and the macroscopic grams, milliliters, kilograms, etc. There is actually a way to bridge those two ideas together. Now, on the particulate scale, we use something called Avogadro's number. Avogadro's number is the number of particles in a mole of that substance. Now, what is a mole, you ask? Well, a mole is a common counting unit that is used by chemists as a way of standardizing the number of particles of something. So, you go to the grocery store. You want to buy a dozen cookies. You walk up to the bakery, you say, "I'd like a dozen cookies, please." And without even flinching, the baker goes back and gives you 12 of those cookies. You go to the dairy section, the refrigerated section, you go and you buy a dozen eggs. Lift up the container, and sure enough, there are 12 eggs in there. A dozen is a collective counting unit that in our system means 12 objects. In the chemical system, a mole is a collective counting object that describes 6.022 times 10 to the 23rd objects. Now, why that number in particular? Well, that is based upon a particular definition. The definition that we use for particles and for mass is dependent upon something called carbon-12, the isotope of carbon that contains 6 protons and 6 neutrons and 6 electrons. And it was determined at one point in time that 12 grams of that carbon-12 contained that number of particles. And that was the basis for our definition for all other kinds of things.
Did you make it for attendance?
So we use the mole as that bridging kind of factor. Because not only can we determine the relationships between moles of stuff and the number of particles of stuff, we'll eventually get to the spot where we can convert between moles of a substance and the mass of a substance as well.
I will be right back.
So going back just a second here. The important thing to draw out of this particular conversation is that our mole is a bridge. Our bridge to connect the world of the microscopic and the number of particles of things and the macroscopic world where we describe things in terms of mass and volume sometimes. We can compare directly the number of particles of an object and the molar mass of an object, the mass that we get off of the periodic table of elements, using moles as that bridge in between. And so what that means is that if I have 1 mole of carbon, I expect that carbon to weigh 12.01 grams. I expect that carbon to have Avogadro's number of carbon atoms. If I have 1 mole of copper, I expect 1 mole of copper atoms, 6.022 times 10 to the 23rd atoms of copper. I expect that to weigh 63.55 grams. Why 63.55 grams? Because that is the mass of copper on the periodic table.
Follow me, down side of me.
So when it comes to moles, we can measure moles for a variety of different substances. We can measure moles for not just atoms, but for molecules as well, or for atoms within those molecules. So with that in mind, let's take a look at this example problem. How many sulfur atoms are in 1 mole of hydrogen sulfide gas?
Stuff from the Dollar Tree that you're gonna give to Chris, just to help you out. Because I was like talking to Amy, I was like, I know like Chris likes like weapons and stuff, but I was like, he's really hard to shop for.
Now,
Like,
the
yeah.
way to approach these problems
Yeah, but at least you just
takes us back to chapter 1 when we were doing dimensional analysis. We're doing unit conversion here. What we're looking for
She's like, you know, just do
are a
that.
series of things that are equal to each other
Just like kind of
that can convert between one another.
Okay, so if I see something that you
And so the
might-
things that we want to look at are 1 hydrogen sulfide molecule would contain 1
Yeah, you can do that.
sulfur atom.
Yeah, I mean, it's just hard because he's not really eating anything right now, so it's like candy's kind of out of the question. So it's like,
Same with alcohol.
yeah,
But you can say that for after school.
that's true. Well, he's already had it. He's just still trying to recover. But yeah, I don't know. I'll see what I can find if it ain't good. Then
Are you about to leave?
Yeah,
Oh, okay.
I'll be back.
And 1 mole of sulfur would contain Avogadro's number atoms. So if I put those two concepts together, starting with my 1 mole of H2S, I know that for every H2S, I get 1 atom of sulfur. And 1 mole of sulfur would contain 6.022 times 10 to the 23rd atoms of sulfur. So my H2S's cancel, my moles of S cancel. I'm left with just atoms of sulfur. I do the calculations here. 1 times Avogadro's number divided by 1 will be Avogadro's number, 6.022 times 10 to the 23rd sulfur atoms. Go ahead. In terms of labeling that as atoms of S. Yes, so that's just it's a labeling thing. If I was asked for atoms of hydrogen, I would just put Avogadro's number atoms of hydrogen. It's more of a stylistic thing than anything. It's just a way of helping me make sure that I'm labeling and I'm finding the right thing. Now, what if I were asked about the hydrogen? How many hydrogen atoms are in 1 mole of H2S? Well, here, conversion is practically the same. The only difference is in the formula. I have 2 hydrogens for every H2S instead of 1. So if I follow my dimensional analysis all the way through, one mole of H2S, 1 mole H2S will give me 2 moles of hydrogen. 1 mole of hydrogen is still Avogadro's number of atoms of hydrogen. And so this time it's 2 times Avogadro's number, which would give me 1.204 times 10 to the 24th atoms of hydrogen. So the process here is incredibly straightforward. It's just taking what we've already done with dimensional analysis and adding some new kinds of conversions that we can use. now involving conversions of the mole. And conversions of atoms within the mole or within the molecule. So using those subscripts to tell us how many atoms of a given element there are per molecule. Now, the other half of this particular dimension is that of mass. As I mentioned before, mass represents the macroscopic world. Mass represents what we can do from the standpoint of things that we can measure in the lab. And so to that end, Avogadro's number gives us some of this information by telling us that a chemical mole of a substance contains within it however much mass is associated with that element on the periodic table. And so not only can we calculate this for a given element, but we can actually combine them to give us the molar masses for compounds simply by adding together the periodic table masses for the elements that make up our substances. So take, for example, carbon. According to the periodic table, the molar mass of carbon is 12.01 grams. So every mole of carbon is going to, on average, weigh 12.01 grams. If I look on the periodic table at oxygen, average mass of a mole of oxygen is going to be 16.00 grams. So if I wanted to know those numbers individually, all I'd have to do is look them up on the periodic table. If I wanted to look up the mass of a compound like carbon dioxide, where I've got one carbon and two oxygens, then all I would need to do is take the mass of a carbon and add to it the mass of two oxygens, again, using the values from the periodic table. Now, for our purposes, as a general rule of thumb, we will be taking molar masses off of the periodic table to 2 decimal places. Why 2 decimal places? Well, primary reason why is to ensure that our molar masses aren't going to limit our significant figures. So if I'm doing measurements, most measurements that I take on a balance or with a graduated cylinder have 3 to 4 significant figures with them. By doing this with the periodic table, I'm going to guarantee that I have at least 3 significant figures in all of my masses. Because the smallest mass on the periodic table, hydrogen, if I go to 2 decimal places, is 1.01 grams. 3 significant figures in total. So in the case of carbon dioxide, I add together the 12.01, I add together the 2 16s, and I get 44.01 grams per mole. And so what that tells me is that if I have a mole of carbon dioxide molecules, so 6.022 times 10 to the 23rd molecules of carbon dioxide, I should expect that group of carbon dioxide molecules to weigh 44.01 grams. And so like I said, now we have an effective bridge between individual particles that are undergoing chemical reactions and stuff that I can actually measure in a laboratory. And the mole is what kind of connects them all together. The mole is the center hub of our wheel of quantitative calculations in chemistry. It all runs through the mole. The mole kind of extends out like spokes on a wheel to different types of calculations that we can do regarding chemistry and quantitative analysis in chemistry. So let's do some practice problems where we calculate some molar masses. If you have a periodic table on you, this would be a great time to break that out. If you don't, that's okay. You're just going to have to follow along as best you can. So, hydrogen. On the periodic table, I get a mass of hydrogen at 1.01. If I was talking specifically about an atom of hydrogen, I would say that that particular atom weighed 1.01 AMUs. If I was taking the molar mass of hydrogen, I would say that it weighed 1.01 grams per mole. For oxygen, each oxygen atom weighs 16 AMUs. So the total atomic mass of an oxygen molecule would be 32.00 AMUs. In molar mass terms, it would be 32.00 grams per mole. So every single mole of oxygen molecules is going to weigh 32 grams. Sodium, if I look at the periodic table, I get a atomic mass of sodium at 22.99 AMUs. One mole of sodium will weigh 22.99 grams per mole. So right away, what do we notice about the relationship between atomic mass and molar mass? It's the same. It's calculated the exact same way. What's the only thing that's different? The unit. If we're talking about individual atoms or individual molecules, we would be using AMUs, atomic mass units. If we're talking about moles, then we're going to talk about in terms of grams and grams per mole. Okay, so NaCl. I'm going to have 22.99 AMUs for sodium, 35.45 for chlorine, 22.99 plus 35.45 gives me 58.54 AMUs, which would be 58 0.54 grams per mole. In water, I have 2 hydrogens, each with 1.01 AMUs, plus oxygen with 16. I would get 18.02 AMUs as a result. And that would mean that my molar mass is 18.02 grams per mole. Yeah. In terms of magnitude, in terms of the number, they are the same. In terms of the unit, they are different. And the reason for that is the AMU is actually defined based on being a part of a mole of a gram. So there is a conversion between AMUs and grams, and basically the conversion is 1 over Avogadro's number. That's what ties the two together. So in the end, AMUs and grams per mole, we're going to get the same number. They just mean different things. Okay, this last one, calcium chlorate. We got to have a calcium, chlorine, and oxygen. Question is, how many of each do we have? How many calciums are we going to have in this compound? Just the one. Molar or atomic mass of calcium is 40.08 AMUs. How many chlorines are we going to have? We're going to have 2. Think about what that number outside of the parentheses means. It means that we need to double everything inside the parentheses. So for chlorine, I'm going to have 2 of those. So 2 times 35.45. How many oxygens am I going to have? 6. It's 2 times 3, 6 in total. 6 times 16.00 here. So I got to do all of that math together. 40.08 plus 2 times 35.45 plus 6 times 16, 206.98 AMUs for an individual molecule. 206.98 grams per mole for a mole of that stuff. Okay, go ahead. When we're doing atomic masses and molar masses, yes, it's always adding the masses off of the periodic table and paying special close attention to what the formula says in terms of how many of each atom there are. And so that's where we got to pay attention to those subscripts. That's where we got to pay attention to those parentheses to tell us how many of those ions we're talking about. All right, so let's see how we're doing. Which of these would contain the greatest number of atoms? A mole of copper or a mole of gold? It's not gold. By the way, it's not copper either. Okay? This is a seemingly trick question. The key word, why you needed to focus in on, we're talking about a mole of each. A mole of each would both contain 6.022 times 10 to the 23rd atoms. So in that case, they would both be the same. We have a mole of each of them, which means we have the same number of particles of each of them. Now, what about this question? Which would have a greater number of atoms, a gram of copper or a gram of gold? Now it's not the same. Moles are standardized. Grams are not. To answer this question, I need to figure out how many moles of each of these substances there are. And the way to do that is with dimensional analysis again. So I've got my one gram of copper. According to my periodic table, there are 63.55 grams of copper in every mole of copper. And so 1 divided by 63.55 would give me 0.016 moles of copper. I compare that to gold, 1 gram of gold. Every mole of gold weighs 197.00 grams. One divided by 197, 0.0051 moles of gold. So which sample contains more moles? It's the copper, which means it's also going to contain more atoms. Yes. Yes, I started to run out of space on the bottom here. Got a little squished. Yes, 197.00 grams of gold in a mole of gold. All right. So when we have to go between grams and moles, it is going to be the molar mass that ultimately forms that bridge. And so if you remember from a previous problem, we determined earlier that the molar mass of carbon dioxide was 44.01 grams per mole. From a dimensional analysis standpoint, remember, this can be viewed as a fraction, 44.01 grams of carbon dioxide over 1 mole of carbon dioxide. And remember, based upon our calculation, we can flip this fraction over if we need to in order to cancel out the units that we want to properly. So in a question like this, convert 10 grams to moles, this conversion is what we would use. 10.0 grams of carbon dioxide is where we start. And so since we have grams of carbon dioxide already in our numerator, our conversion would put them into the denominator, 44.01 grams of carbon dioxide in 1 mole of carbon dioxide. My grams of carbon dioxide cancel. I'm left with just moles. 10 divided by 44.01 to 3 significant figures would give me 0.227 moles of carbon dioxide. Now, if I need to go the other way, if I need to flip it around, it's the same kind of conversion, just flipping over that fraction. 0.500 moles of carbon dioxide every mole of carbon dioxide weighs 44.01 grams. My moles of carbon dioxide cancel. 44.01 multiplied by 0.5 gives me 22.0 grams of carbon dioxide. So what I'm going to do is I'm pretty much going to publish 2 short videos for Monday. It's not going to be one long extended video. The 2 topics that we need to cover are kind of different from each other. And so I think it would be best to split them into smaller chunks. And so what I'm going to do, the first video is going to be a lot more of this kind of stuff. More examples of calculations of conversions between moles and grams and moles, and integrating some of that particle stuff in there as well. The second video is going to be about empirical formulas, which is how we go from this information and we kind of bring in some of that percent composition stuff that we did on Wednesday as well. So it'll be 2 videos. Total time will be about a lecture, about 50 minutes or so. I'll publish them in an announcement. I'll also put them up on my YouTube channel as well. That will be your class for Monday, along with the section 4.2 post-lecture, and that'll carry us through until we meet again in person next Wednesday. Don't forget about the assignments that are due over the weekend. Go ahead and tackle that ions proficiency as best you can. Have a good weekend.